This is problem set 22, where we're going to take some time to talk about some applications of molecular orbital theory in the real world, and just to understand it better, a little bit better conceptually. So what are the differences between hybrid orbitals discussed in valence bond theory and molecular orbitals of MO theory? Okay, so the biggest thing that I think of when I think about this is that hybrid orbitals are atomic orbitals, meaning when an atom comes to a molecule, maybe it hybridizes its orbitals, but those orbitals still belong to an individual atom, and as a result, the electrons belong to individual atoms. So in molecular orbital theory, they're molecular orbitals, right? Those orbitals don't belong, and the electrons don't belong to individual atoms anymore. They belong to the entire orbital. So hybridized orbitals, those mix atomic orbitals together to make new atomic orbitals. Molecular orbital theory takes atomic orbitals and mixes them together to make molecular orbitals. So, good distinction to make. Describe the strengths and limitations of molecular orbital theory with regards to calculating bond energies. So it's possible to calculate bond order or bond energies, unlike valence bond theory, which we don't do that. It is possible in molecular orbital theory, but it requires some computing power. Okay, so it's not something that you can just do by hand. Calculating bond order, it's very good at calculating bond order. Magnetic, great. And geometries, not so great. If you were to use a computer, solve the Schrodinger equation based on molecular orbitals, you could figure out the geometries, but it's not nearly as easy as drawing out the Lewis structure and using valence bond theory and VSEPR to figure out the geometries. Now, if you're confused about how to calculate bond order or how to calculate magnetic properties, I would direct you to my video on problem set 21, where we do that, a lot of that. Using MO theory, explain the differences between a conducting metal, a semiconductor, and an insulator. Drawing MO diagrams may help. All right, so this is a good concept to dive into. So we know with molecular orbitals, in an atom, like if I were to draw a molecular orbital diagram, for example. So this is sigma, sigma, pi, sigma. Right, we've got all these orbitals and we fill them up. Let's say I fill them up like that. We know that this orbital is my HOMO orbital and this is my LUMO orbital. In other words, this is my highest occupied molecular orbital. This is my lowest unoccupied molecular orbital. Well, if electrons are going to be jumping, they're most likely to be jumping between these two orbitals, the HOMO and the LUMO. Now, this is the molecular orbital diagram for two atoms. Okay, but you can imagine if you had 3 atoms, you would end up with more orbitals. If you had 4, you'd end up with even more. And remember, when we talk about metals, we usually refer to them as a sea of electrons. In other words, all of the atoms in a copper wire are forming one giant molecule of copper. As a result, when we get metals, we have the HOMO band and the LUMO band, but we have a ton of them. Or I should say the HOMO and the LUMO orbitals, but we have a ton of them. So imagine if I just drew, right, 1 mole is 6.02 times 10 to the 23rd. So imagine all of those orbitals. Okay, we don't refer to them as orbitals anymore. We start referring to them as bands. And in metals in particular, we call the HOMO, because it has electrons in it, we call this the valence band. And the LUMO we call the conduction band. So if I were to draw this, this is the valence band, and this is the conduction band. The valence band has a bunch of electrons in it. And if I want to move electricity through a metal, I'm going to put electrons in on one side, and it's hard for electrons to move in the valence band. But if I can put in enough energy to excite it to the conduction band, all of a sudden, bam, there's a bunch of space where it can move. And that's why we call it the conduction band, is because when we're conducting electricity, we typically say that electrons are moving through the conduction band. So what's going to prevent conduction of electricity? Well, if this gap is too big, we call it the band gap. If it's too big, it's going to take way too much energy to move electrons through the metal. Okay, so the problem wants us to differentiate between a conducting metal, a semiconductor, and an insulator. This is the difference. Conductors have their valence band and their conduction band overlapping in terms of energies, meaning it takes pretty much no energy for an electron to move up from valence to conduction. So as soon as you put any electricity into that wire, electrons are moving. An insulator then has its valence band and its conduction band, but there's a big energy gap between them. So it's very difficult to move electricity from the valence up to the conduction to allow them to move. Which means a semiconductor has just a small gap. So that's the difference. This is really the answer to the question. That's the difference between conductor, semiconductor, and insulator in terms of molecular orbital theory. And we just call them, instead of calling them homo-lumo, in this context we call them valence band and conduction band, but they mean the exact same thing. Awesome. So let's do some application of this. We also need to talk about what it means to dope our metals. So let's talk about that a little bit. Let's say that we have a block of silicon. Silicon is right under carbon. It's got, actually I won't do that, it's got 4 valence electrons, and it can form a nice tetrahedral structure, lattice, the same way that carbon does. Hopefully that makes sense. Silicon is a semiconductor. So let's say that we have this silicon, and we want to make this silicon more conductive, because right now, this is my valence band. If I want to conduct electricity, I need to excite electrons out of these nice interlocked tetrahedral geometries. I need to excite those electrons out of those geometries into the conduction band. Well, that might be difficult. So maybe silicon on its own doesn't conduct very well. But we can dope the silicon with, let's say, phosphorus. How many valence electrons does phosphorus have? It has 5. So while it's going to fit in this structure, it's also going to have an extra electron right there. Well, that extra electron is negatively charged, so we call this N-type doping. And that extra electron is now easier to excite up to the conduction band because it's not locked into the geometry with all the other electrons. Now I can choose how much phosphorus I want to put in my silicon. And when I do that, as I increase the concentration of phosphorus, what do you think that does? It increases the conductivity of this semiconductor. Now when we do that, just make sure I explain this well. When we do that, what we say is we take some of this valence band and we bring the energy of those phosphorus electrons is closer to the conduction band. So this is what an N-type, you could, right? This is what an N-type semiconductor or a negatively doped semiconductor looks like. So then you can imagine that we could do the other. So if I were to, actually I can just do this. Let's just copy that, paste it right there. Okay, what if instead of phosphorus, I decided to dope this not with phosphorus but with boron. how many valence electrons does boron have? It has 3. So it can't totally fit in this lattice. So the way I'm representing that is it's fitting in this lattice, except it has holes where it should have electrons participating in the lattice, but it doesn't. Well, if there's a hole there and I put electricity into one side of this whatever, okay, electrons, this electron right here could get pushed into that hole, and now there's a hole here. And this electron can get pushed into that hole, and this electron can get pushed into that hole. And so the holes allow electricity to be conducted through the valence band. And the way we draw that is we say the energy of the quote-unquote conduction band gets lower. Now remember that we're just drawing these in terms of energy, right? The conduction band isn't higher than the valence band. It's just like the energy state of the electrons being conducted. And so we can lower that, meaning that we can conduct at a lot lower energy electrons because we don't have to push them up to the conduction band. Okay, so this, because boron is deficient 1 electron compared to silicon, this is called p-type, or positively doped. All right, so there's a little intro to doping. So we're given a bunch of different metals here, right? And they want us to match those metals to one of these pictures. So let's just talk about what these pictures mean. This picture means, let me just make sure I explain this well. So this picture A means that we've got overlapping valence and conduction bands. This second picture let me just give me a second to figure this out exactly. Okay, so let me explain this a little bit better. In this case, our valence band or for copper, well, this is showing that the valence band is not totally full of electrons. So I'll say partially filled valence band. Here we have a totally full valence band, and so there's but the conduction band is very close, and so this is just overlapping bands. That's what this picture is trying to draw. Sorry, it took me a second to figure that out. All right, here we have a little bit of a gap, so this would be a semiconductor. I know a little bit is relative, but relative to this, right, this is a huge gap, so this would be an insulator. Okay, and then here, if you remember, N-type is bringing the energy of the conducting band lower, so this is N-type, and P-type is bringing the energy of the valence band higher. Awesome. So now we just want to apply that to some of these substances. So copper. Copper, if you think about it, if I was to draw the electron configuration, copper is argon, 4s1, 3d10. Okay, that 4s1 suggests that the valence band is not full. Okay, so you can, because it's not full, you could conduct electricity through the valence band. So this is like, it's like partially filled up valence band. Okay, so copper would be represented by A. Magnesium is a metal, and magnesium, its electron configuration is neon 3s2. That means that that orbital is full, which means it's a metal, which means it can conduct really well. Okay, but it's that valence orbital is full, so that would be represented by B. Silicon is a semiconductor, and if it's not doped, it's just going to look like C. Sodium chloride. Sodium chloride is NaCl. That's like a salt. Okay, so that's not a semiconductor. okay, at all. That's an insulator, and so that's going to be represented by F. Okay, at this point I'm actually going to pull up the periodic table. Now, in case I didn't explain this well, semiconductors follow along this metalloids line. Okay, so silicon is a good semiconductor because it's along that metalloids line. I didn't mention that for C. All right. Gallium arsenic. Okay, this is interesting. So silicon is a good semiconductor because it's kind of got those it can form that nice tetrahedral lattice, right? Germanium can do the same thing, right? Each germanium atom has 4 valence electrons. Each silicon atom has 4 valence electrons. But we also have this thing called a compound semiconductor. Okay, and germanium arsenic is an example of that. So, sorry, gallium arsenic. So gallium has 3 valence electrons. Arsenic has 5 valence electrons. So for every gallium arsenic combination, you get 8 total valence electrons, which is like 4 valence electrons for each. And so gallium arsenic is a compound semiconductor. It's going to behave like a semiconductor. And for that reason, it is just represented by C. All right, then we get silicon doped with phosphorus. So compared to silicon, phosphorus has an extra electron, so that's n-type, and n-type is D here. And silicon doped with gallium, compared to silicon, gallium is missing an electron, so that's positive, so that's represented by E. Okay, maybe that was a little bit confusing. If you rewind and watch through it again, maybe it'll make a little more sense. But hopefully that helps you understand at least a little bit about how we can represent the valence and conduction bands for semiconductors, insulators, metals, and then doped semiconductors. All right, the rod cells in the eyes absorb 498 nanometer light. What is the energy difference in joules between the HOMO and LUMO of the retinal that absorbs this light? Okay, so I'm going to jump over here I'm going to jump up here to this picture. Just going to bring it down here. So we've got this picture of a molecular orbital theory diagram, and we have the HOMO and we have the LUMO. Now, if we're absorbing 498 nanometer light, that means that a photon is coming in. I'll draw in a different color. Photon is coming in, hitting these electrons and bumping them up, exciting them to the next energy level. Okay, so if we know that this photon has an energy of 498 nanometers, then we know that, it has a wavelength of 498 nanometers. Then if we can find the energy of that photon, then we'll know the gap between the HOMO and the LUMO. Okay, now we've done this before. We know that the energy equals hc over lambda. So hc over 498 times 10 to the negative 9. And that gives me an energy of 3.99 times 10 to the negative 19 joules. Okay, so for the rod cells in our eyes, the gap between the HOMO and the LUMO is about 4 times 10 to the negative 19 joules, because our rod cells absorb that energy of light. All right, acetylene or ethine, C2H2, is a highly flammable hydrocarbon used in welding, oxoacetylene torches, etc., because of the extremely high temperature the flame produced. Below is a MO energy diagram for the CC bond in acetylene. Knowing that each carbon atom uses one of its 4 valence electrons to form a sigma bond with the hydrogen atom, fill in the MO diagram for the CC bond. Okay, kind of confusing here. Let's draw a picture of acetylene, C2H2. C2H2 looks like this. Okay, so what's confusing about this problem is we are not doing the MO diagram for acetylene. We're doing the MO diagram for the CC bond in acetylene, just this part. So while each carbon, So these are each carbon here, the atomic orbitals for carbon. Well, each carbon has 4 valence electrons. It says here, knowing that each carbon uses one of its 4 valence electrons to form a sigma bond with hydrogen, fill in the MO diagram for the CC bond. Well, if each carbon uses 1 electron for bond with the hydrogen, how many electrons does each carbon have left for the CC bond? And that answer would be 3. So we've now put in the atomic electrons for each carbon. Now, the other well, let's see. Fill in the MO diagram for the CC bond. So now we just say, all right, I've got 6 total electrons, so I just fill up 1, 2, 3, 4, 5, 6. Now, the confusing thing about this diagram is it is kind of combining the hybridized orbitals of valence bond theory with molecular orbital theory. So what it's saying is CC, we know is each of these carbons is sp hybridized. It's going to have, each of them has 1 sp orbital going over to the H and 1 sp orbital going between the two to form the sigma bond. Okay, in valence bond theory. In this case, these sp orbitals are going together to form a sigma orbital. You see it labeled there sigma, and a sigma star orbital. Okay. But then we also know that if it's only sp hybridized, each carbon still has 2 p's left, okay, which are drawn here, which are then forming pi orbitals and pi star orbitals. Okay, so this is you could think of, this is a sigma orbital made from sp hybridized orbitals. Label the molecular orbitals, sigma, sigma star, pi, pi star. They're already labeled on mine, though I don't think they are on yours. Okay, and remember, if there's 1 line, it's sigma. If there's 2 lines, it's pi. And that each sigma has a corresponding sigma star higher energy, and each pi has a corresponding pi star at a higher energy. Is it diamagnetic or paramagnetic? Well, if I look at this, everything has a partner, so that's going to make this diamagnetic. What's the bond order? Bond order is bonding minus anti-bonding divided by 2. I've got 2, 4, 6 in bonding minus none in anti-bonding divided by 2 gives me a bond order of 3, which is supported by our structure here. Now, it won't always be, and in the case that they're not the same, molecular orbital theory is more correct. Right, during combustion of acetylene, the carbon-carbon bond is broken. Should it take more or less energy to break the carbon-carbon bond in acetylene than in ethane? All right, then we need to know what ethane is. Ethane is just 2 carbons with a single bond. Okay, and what about ethene? Ethene is 2 carbons with a double bond. And then acetylene, also known as ethene, or ethyne, is 2 carbons with a triple bond. So which one's going to take the most energy to break? Well, acetylene takes the most energy to break. Why? Because it's got a bond order of 3 versus 2 and 1. Higher bond order is stronger bond, so it'll take more energy to break. This is kind of a mixture idea. I wouldn't worry too much about understanding how the hybridization plays in. You should be able to count up the electrons and should be able to count up the electrons from the atomic orbitals, stick them into the molecular orbitals, and answer all of these questions. All right, so there's just some applications of molecular orbital theory. I think that was everything. Yep, it was. Good luck.